So in this video, I am going to explain about chemical bonding and molecular structure worksheet questions. So here also I have selected some important models. We will discuss one by one. First question, the hybridization and shape of I3 minus ion respectively are. So we know I3 minus can be written as I2 minus. So your structure will be like this, 3 lone pairs. Here I minus and here I. So around I minus 3 lone pairs plus 2 bond pairs. Hybridization will be sp3d. Actual geometry is trigonal bipyramidal, but due to the presence of lone pairs, it assumes linear shape. That means hybridization is sp3d and linear. So option B. Next question. The correct pair of species which are not isostructural is. If you take BRF5, this will be sp3 D2 hybridization and the geometry will be like this and one lone pair. Square pyramid and XCF4, let here XCF4 and two lone pairs. This is also sp3 D2 hybridization, square planar. So these two will be having different structures. So first one is square pyramidal and the second one is square planar. Both are sp3 D2 hybridization. So therefore the correct pair of species which are not isostructural, that means same structure, not having same structure, are D option, BRF5 and XCF4. Both are having different structures. Next one. This is based on MOT, molecular orbital theory. Identify all the species that do not exist. That means simply do not exist means bond order will be 0. So here in case of Li to 2 minus, bond order will be equal to 0. So a total number of electrons 8. That means number of bonding electrons equal to number of anti-bonding electrons. Therefore bond order 0. Next, Ne2, noble gas, does not exist. He2 also noble gas, which does not exist. So for this also bond order equal to 0. Here also bond order equal to 0. That means simply bond order 0 means number of bonding electrons equal to number of anti-bonding electrons. Here also same condition. So therefore Li2 2 minus Ne2 He2 does not exist. So formula to calculate bond order is half into number of bonding electrons minus number of anti-bonding electrons. From this we can calculate bond order. So based on bond order formula, Li2 2 minus Ne2 and He2 do not exist. Therefore option B. This is based on molecular orbital energy diagram. Next one. Here the incomplete Lewis representation of CO3 2 minus is given. The formal charge on atoms marked A, B, C respectively are. Here structure is given like this. O and double bond O. Here carbon is marked as A and this option B, this option C. And total 2 minus. You have to calculate formal charge. Formal charge formula, number of valence electrons in free atom minus number of electrons in lone pairs minus half into number of bonding electrons or shared electrons. So here we can calculate formal charge of carbon, number of valence electrons 4 minus number of lone pair electrons 0 for carbon if it is having 4 bonds. So half into number of bonding electrons 2 plus 2 plus 2 plus 2. That means 8. Therefore formal charge will be 0. So A is 0. Therefore A will be 0. Next, formal charge of oxygen, which is star marked. See here star marked. Number of valence electrons 6. So number of lone pair of electrons here 2 lone pairs will be there. 2 lone pairs and this is star mark. That means total 4 electrons minus half into number of bonding electrons 4. 2 bonds 4 electrons. That is B also equal to 0. Next, formal charge of one more oxygen. So here 3 pairs will be there. So number of valence electrons in oxygen atom 6. Next, lone pair of electrons again 6 minus half into just one bond means 2 electrons. Therefore, C will be equal to minus. So A is 0, B is 0 and C is minus 1. Therefore, option A. Formal charge, very very important question. Here two types of oxygen, star marked oxygen and normal oxygen. For star marked oxygen, formal charge is 0. For normal oxygen, minus 1. So dipole, induced dipole interactions are present between which are the following pairs. If you take NH3, it is polar molecule. In case of polar molecule, dipole will be present. Next, if you take H2, non-polar molecule, induced dipoles will be present. So induced dipoles are also known as London forces or dispersion forces. That means in case of non-polar molecules, induced dipoles or London forces or dispersion forces are present. Therefore, between NH3 and H2 there will be dipole and induced dipole interactions will be present. Option C. This is common question for states of matter and chemical body. In case of NH3, permanent dipole moment is present, therefore it is dipole. In H2, there will be no dipole moment, therefore non-polar molecule. In case of non-polar molecules, induced dipoles will be present. So between NH3 and H2, dipole, induced dipole forces will be present. Next. The correct order of CO bond length is. So here three molecules are given. CO, the structure of CO, carbon monoxide. So for this, bond order is 3. So in a bond order is number of bonds between two atoms. Next, CO2 is given. Bond order equal to 2. So between two atoms, two bonds are present. Next for CO3, 2 minus. Structure will be like this. So in this molecule, resonance is present. Resonance. You can calculate bond order like this. These structures are possible. 3 resonating structures. Structure 1, structure 2 and structure 3. So bond order in case of resonating structures. Number of bonds between two atoms in all the forms. Number of bonds between two atoms in all the forms by number of forms. So therefore, bond order equal to number of bonds between two atoms in all the forms. That means here I am selecting these two atoms. So between these two bonds are present. Next, between these two, one bond is present. Between these two, again one bond is present. Therefore, 2 plus 1 plus 1, 4 by number of forms 3. So which is equal to 1.33 bond order. So here the order of bond order is bond order CO, next CO2 and CO3 2 minus, and therefore the order of bond length is reverse. CO, CO2 and CO3 2 minus. So since bond length inversely proportional to bond order, therefore cut option D. CO bond length will be highest for CO3 2 minus, least for CO. So first calculate bond order for three species. CO bond order 3, CO2 bond order 2, CO3 2 minus due to resonance special molecule 1.33. So first I am writing order of bond order. CO highest, CO3 2 minus least. Then order of bond length reverse to bond order. Next question. Number of H2O molecules participating in hydrogen bonding in CuSO4.5H2O. So here it is given CuSO4.5H2O, copper sulfate pentahydrate. This is hydrated salt. So actual structure of this molecule is CuH2O 4 times 1H2O and SO4. This is the actual structure. Remember this. So how many water molecules are participating in hydrogen bond? So here structure will be like this. Cu H2O can be written like this. OH2. 4 water molecules are bonded with. Here Cu will be in Cu2 plus state. Outside one water molecule, and here SO4 2 minus. This is the actual structure. So 4 water molecules are bonded with Cu2 plus with day 2 bonds. This is day 2 bond. And this water molecule can participate in hydrogen bond. So therefore, the number of water molecules participating in hydrogen bonding are only 1. Therefore, option C. So very important. 4 water molecules are bonded with CO2 plus with day 2 bonds, and one water molecule outside of complex. So this will be complex. So this outside water molecule can participate in hydrogen bonding. Therefore, only one water molecule. Next. A direct question which is based on intermolecular forces. The dipole-dipole interactions energy between stationary polar molecules and rotating polar molecules. Direct question, NCERT question. So dipole-dipole interaction energy. First case, stationary. Polar molecules. And the second one, rotating polar molecules proportional to here 1 by r power 3 and here 1 by r power 6, where r is distance between two molecules. Direct question for option B. Dipole-dipole interaction energy in case of stationary, that means not moving. Molecules will be at rest. That interaction energy directly proportional to 1 by r cube. In case of rotating polar molecules, directly proportional 1 by r power 6. Here r is distance between two molecules. The shape of BrF5 and XCF4. First BrF5 sp3d2 hybridization. You can write structure like this. F5 and one lone pair will be there. So geometry, square pyramidal, Similarly, HCl for xenon tetrafluoride. So 4 bond pairs and square planar. Here also sp3 D2 hybridization. So first one square pyramidal, second one square planar. So option D. Here 5 bond pairs, 1 lone pair. Here 4 bond pairs, 2 lone pairs. Next one. So correct sequence of bond order is here given O2, 2 minus, O2 minus, O2 and O2 plus. So based on molecular orbital theory, you can calculate bond order. How to calculate bond order? Half into number of bonding electrons minus number of anti-bonding electrons. So from this we can calculate O2 2 minus will be equal to 1 and here 1.5 bond order, O2 2 and here 2.5. So therefore order of bond order, correct order of bond order is, so first one O2 plus greater than O2 greater than O2 minus, which is greater than O2 2 minus. So correct option B. So by using this formula, we can calculate from molecular orbital energy diagram. Remember these examples, very important. So as the positive charge on O2 increases, bond order also increases. The positive charge on O2 increases, comma bond order also increases. Remember like this simply. Next question. Find out the correct hybridization of central atom in BCl3, PCl5, NH3 and NF6. So BCl3. So hybridization of BCl3 sp2 and which is planar. PCl5 will be like this. Trigonal bipyramidal. Next NH3, one lone pair. Pyramidal. Next SF6. We have let hybridization here. Here sp3 D, here sp3 and SF6 will be like this, octahedral. sp3 D2. sp2 bcl3 sp3d bcl5 sp3nh3 sp3d2 sf6. Remember here geometry solves. So your option B, sp2 sp3d sp3 and sp3d2. Next, so which are the following molecules does not exist according to molecular orbital theory? So molecule does not exist means bond order will be half into number of bonding electrons minus number of anti-bonding electrons will be equal to 0. Does not exist. So here for Ba2 number of bonding electrons will be equal to number of anti-bonding. Therefore bond order equal to 0 for Ba2. Therefore Ba2 does not exist. Option B. So total 8 electrons will be there. 4 in bonding orbital, 4 in anti-bonding orbitals. Therefore bond order will be 0. There will be no bond formation between two beryllium atoms. Next question. So find out bond order in case of He2, He2 plus, O2 and O2 plus. So for He2, bond order equal to 0 because number of bonding electrons equal to number of anti-bonding electrons. Next for He2 plus. So here total number of electrons in He2 are 4 electrons. He2 plus means 3 electrons. 3 electrons means bond order equal to half into bonding electrons 2 minus anti-bonding 1, that is 1 by 2. 1 by 2 is 0.5. So here bonding electrons more than anti-bonding. Next for O2, bond order equal to 2, standard example. Next for O2 plus, bond order equal to, already have given this value, 2.5. From molecular orbital theory diagram, MOED diagrams. Check here. For He2, 0. For He2 plus 0.5. For O2, 2. And O2 plus 2.5. Therefore, option D. Next one. Here matching sp3d. So for option A, sp3d means PCl5. Correct? PCl5. Next for B, sp3d2 SF6. So PCl5 is present in fourth option. Next SF6, it is present in second option. For C, DSP2. So most of the platinum complexes are DSP2 square planar. That means PT Cl4 2 minus. It is present in 1. Next option D, sp3d or dsp3. It is present in ClF3. ClF3 present in option 5. Therefore, A4, B2, C1 and D5. Therefore, option A. Option A. 4215. Here we can write DSP3 also. Okay, next question. In which of the following hydrogen bonding is strongest? So hydrogen bonding is strongest if hydrogen is attached to most electronegative element F minus. Next O minus. Next N minus. So electronegativity value 4, electronegativity 3.5 and here electronegativity 3. Here in this direction electronegativity increases. Therefore hydrogen bonding strength also increases. Strength of hydrogen bond increases. So clearly from options D, here delta plus and here delta minus will be there. If there is hydrogen bonding between hydrogen and fluorine, that will be strongest. Therefore D. So strength of this hydrogen bonding will be 10 kilocalories per mole. To dissociate this hydrogen bonding, 10 kilocalories of energy is required. Strongest. Next. As per molecular orbital theory, the pair of molecules which do not exist. So clearly for Ba2 and Na2, number of bonding electrons will be equal to number of anti-bonding electrons. Therefore, according to bond order formula, number of bonding minus number of anti-bonding, bond order will be equal to 0. Therefore, these two molecules do not exist. Option D. Based on diagram. MOID diagram. Molecular orbital energy diagram. Next one. So identify the pair of spaces with the same geometry. This is most important one. Take Xe F2, which is sp3d hybridization, 3 lone pairs, 2 bond pairs, linear geometry. Similarly, I3 minus or you can write I2 minus. These two are isostructural and I above the plane, below the plane, I minus. This is also linear. So here 3 lone pairs plus 2 bond pairs. Here also same. 3 lone pairs, 2 bond pairs. Same hybridization sp3d. These two are having same geometry. Option D. Both are linear molecules. Tetraatomic molecules are ions with different shapes. Different shapes. check here. SF4 NH4 plus. I will let SF4 sp3 dehybridization. Take here SF4, which is sp3 dehybridization. You can write structure like this. One lone pair, 4 bond pairs will be like this. Seesaw geometry. 4 bond pairs, 1 lone pair. Next, NH4 plus, NH4 plus sp3. 4 bond pairs, 0 lone pairs. On nitrogen plus. Tetrahedral. So these two are having different geometries. So option C. So hybridization, geometry, number of lone pairs, bond pairs, all are important. So here 4 bond pairs plus 1 lone pair. Here 4 bond pairs and 0 lone pairs. Next question. Formal charge concept. Formal charge of atoms 1, 2, 3 in O3. And I will use structure. Structure will be like this. Here 3 pairs and here 2 pairs. So this is atom 1, this is atom 2 and atom 3. 3 types of oxygens. Formal charge, we know formula. Number of valence electrons in free atom minus number of lone pair of electrons minus half into number of bonding electrons or shared electrons. So based on this, I will calculate formal charge of say O1. Number of valence electrons 6 minus number of lone pairs 4. Lone pair of electrons 4. Half into number of bonding electrons 4. 2 bonds. Therefore, formal charge will be 0. Next, formal charge of O2. 6 minus on second 1 lone pair, therefore 2 electrons. Minus half into number of bonding electrons, 3 bonds. 3 bonds are attached, 6. So which is plus 1. Next, formal charge of O3. 6 electrons minus again 6 electrons. Lone pairs 3. Therefore 6 electrons. Minus half into 1 bond, 2 electrons. Therefore minus 1. So respectively 0, plus 1, minus 1. Therefore option B. Next question. Bond lengths of C2, N2, B2 molecules are X1, X2, X3, PM, that means picometers respectively. The correct order of bond length. First we can calculate bond order. So for C2, bond order equal to half into bonding electrons minus anti-bonding electrons. So for C2, total number of electrons 12. We can fill 12 electrons. That is like this. 2 electrons, 2 electrons, 2 electrons, 2 electrons. Total 8, 9, 10, 11, 12 electrons. So bond order equal to, here this is bonding molecular orbital, bonding molecular orbital, and this one also bonding molecular orbital. So total number of bonding electrons 2 plus 2 plus 2 plus 2, that is 8, minus anti-bonding 4, that is simply 2 bond order. Similarly for N2, so I will write formula here. for N2. We know for N2 bond order is 3. 3 bonds between 2 nitrogen atoms. Clear. Next for B2, you can calculate for B2. So total number of electrons, 10 electrons. We can fill electrons like this. Total 2 electrons, 2 electrons, 2 electrons, 2 electrons and 1, 1. So therefore bond order equal to half into bonding electrons. This is bonding molecular orbital and this one also bonding molecular orbital. This one also bonding molecular orbital. Total 2 plus 2 plus 2, 6 minus 4. That is 2 by 2, 1. Bond order 1. So therefore, and we know bond length inversely proportional to bond order. Remember this. So bond order is highest for N2. Therefore, bond length will be least. Therefore, order will be A. So if bond order increases, bond length decreases. So for C2, bond order 2, N2 3, B2 1. So bond length order X3, which is X3 B2. Next X1, X1 is C2. Next X2 N2. N2 highest bond order, therefore least bond length. Next one. Hybridization of nitrogen in NO3 minus NO2 minus NH4 plus. So hybridization formula. Remember this one, very very important. So number of surrounding atoms plus half into group number of central atom minus valency of central atom with respect to surrounding atoms minus charge of cation plus charge of anion. In this way we can calculate. Therefore, for NO3 minus hybridization equal to number of surrounding atoms 3 plus half into group number of central atom 5 minus valency of central atom with respect to surrounding atoms. In case of oxygens, double the number of oxygen atoms becomes valency. 6. Here minus 1 means take plus 1. Therefore 3. 3 means here sp2. So 1 S and 2 P. Next similarly for NO2 minus hybridization equals surrounding atoms 2 plus half into group number 5 valency with respect to oxygens double plus 1 which is equal to 3 again sp2. For NH4 plus hybridization equal to surrounding atoms 4 plus half into group number 5 valency with respect to hydrogens means take same number of hydrogen atoms. That means 4 plus 1 means minus 1. Therefore, that is equal to 4 sp3. sp2, sp2, sp3. Option A. Next. Bond order is an inverse measure of. So we know bond order is the number of bonds between two atoms. bond order. So bond order directly proportional to bond dissociation energy or stability or bond energy. Next, bond order inversely proportional to bond length. Remember these two. That the bond order increases, bond dissociation energy or stability increases. If bond order increases, bond length decreases. Therefore, bond order is inverse measure of bond length. Therefore, option A. Next. Which compound among the following have a permanent dipole moment? See here, first molecule. So dipole direction in this direction, in this direction, and here in this direction, in this direction. So all are different. These two are identical and these two are identical. And four are not equal. Resultant dipole moment will be in this direction. Resultant dipole moment. Therefore, resultant dipole moment not equal to 0. Therefore, it is polar molecule. Dipole moment not equal to 0 means there will be dipole moment. Next, for C double bond C, here Cl and Cl, H and H, dipole moment will be like this. This is center of the molecule, dipole moment and dipole moment. And here in this direction, in this direction. So equal and opposite vectors acting on same point. Dipole moment resultant will be equal to 0. Therefore, non-polar molecules. There will be no dipole moment for this molecule. Similarly, we are. This is center of the molecule. Dipole's direction. This is center of the molecule. Resultant dipole moment equal to 0. Non-polar. There will be no dipole moment for non-polar molecules. For polar molecules, there will be dipole moment. Therefore, option 1 has permanent dipole moment. CCl bond is more polar when compared to CH bond. Therefore, resultant moment will be in right direction. Next. So, in which of the following molecules are ions? The central atom is sp2 hybridized. sp2. So, apply hybridization formula. So, first take number of surrounding atom. I am calculating for BF3. Number of surrounding atoms 3 plus half into group number of central atom 3 minus valency of central atom with respect to surrounding atoms. Number of fluorines equal to valency, that is 3. Therefore 3 hybridization sp2. Next, for NO2 minus, hybridization for NO2 minus surrounding atoms 2 plus half into group number 5 minus valency with respect to oxygen atoms, double the number 4 and plus 1. It will be equal to again 3 sp2. So in C option, both the molecules, that means first molecule and ion will be having same hybridization, sp2. In remaining options, you will get sp3 also. Next question. The linear shape of CO2 is due to. So CO2 structure will be like this. C double bond O and double bond O. So here one sigma, sigma, and here pi, and this is also pi, and here two pairs, and here also two pairs. So here carbon atom around carbon 2 sigma 2 pi. Therefore, carbon atom undergoes sp hybridization. Sp hybridization, the geometry linear or linear shape. So clearly option B. So for this molecule also resultant dipole moment will be equal to 0. Therefore, even though it contains polar bonds, total molecule will be non-polar. Dipole moment will be 0 due to sp hybridization, linear geometry. Next. So which factor makes Li the strong reducing agent in aqueous solution? Lithium is the strongest reducing agent. Lithium will be changed to Li plus. This will be ionization, and when it interacts with water, it gives Li aqueous plus. So this process will be hydration energy. So when hydration energy is always negative, that is exothermic. Ionization energy is positive, which is endothermic. So here hydration energy is dominating over ionization energy. So here more negative value. So Li plus aqueous is stable due to high hydration energy. High hydration energy means delta H hydration energy will be more negative value. So more negative value of hydration energy, more stable. Therefore, Li will be converted to Li plus aqueous easily. That means spontaneous process. That means Li is reduced. So Li is oxidized. Sorry. Li is oxidized. Therefore, Li acts as reducing agent. So due to high hydration energy, that means more negative value of hydration energy, lithium is easily oxidized. Therefore, it acts as powerful reducing agent. Options. Here dominating factor is hydration energy. Next. So dimerization of solute molecules in low dielectric constant solvent is due to. Simply, I will take acetic acid in benzene which is low polar solvent or low dielectric constant undergoes dimerization like this. Dimer. This dimerization can be explained by using hydrogen bonding. I'm writing here hydrogen bonding dotted lines, hydrogen bonding and hydrogen bond. This is dimer. Dimer of acetic acid. So due to hydrogen bonding. Therefore option will be A. So dimerization is due to hydrogen bonding in low polar solvent or low dielectric constant solvent. Next one. In oxygen and carbon, the bonding is. So we know in oxygen, O double bond O is present, two pairs. Here one is sigma and other one is pi. Therefore one sigma and one pi bond is present. Next in C2 molecule, so total number of electrons 12 electrons. We will write molecular orbital diagram. Molecular orbital diagram of C2 12 electrons 2 plus 2 plus 2 plus 2 8 9 10 11 12. So this is bonding molecular orbital and bonding molecular orbital. So this is pi. So in pi bonding molecular orbital, there are in pi bonding molecular orbital, the number of electrons equal to 4. There will be formation of 2 pi bonds. Therefore in C2, 2 pi bonds are present. Therefore option A. In pi bonding molecular orbital, 4 electrons means they can form 2 pi bonds. This is also important. Which of the following is an incorrect statement? So hydrogen bonding is stronger than dispersion forces. So when compared to dispersion forces, hydrogen bonding is stronger due to more force of attraction. Sigma bonds are stronger than pi bonds. That is also correct. Ionic bond is non-directional due to just electrostatic force of attraction between cations and anions. Next here, sigma electrons are referred to mobile electrons. Here sigma is not given. Write sigma. Sigma electrons are referred to as mobile electrons. So sigma bond is strong and electrons are tightly held between, if you take hydrogen and hydrogen, this is sigma bond. Two electrons are tightly held between two atoms. So sigma bond is very very strong. Therefore, there will be no movement of electrons. Therefore, D option is incorrect. If it is pi bond, there will be delocalization. That means, write like this. C double bond O, double bond O. Pi bond will be migrating like this. O minus, or from this direction. C double bond O and O minus. So pi bond will be delocalized. There will be no movement of sigma electrons due to its strong nature. Due to weak nature, pi bond will be delocalizing between different atoms. Therefore, D option wrong. Next. The percentage of S character in hybrid orbitals of nitrogen in NO2 plus NO3 minus NH3. First take NO2 plus hybridization is equal to number of surrounding atoms 2 plus half into group number of central atom 5. Valency with respect to oxygens double the number 4 plus 1 means here minus 1. That is equal to 2. 2 means Sp. NO3 minus hybridization equal to surrounding atoms 3 plus half into group number minus valency with respect to oxygens double the number 6 plus 1. That is 3. 3 means Sp2. In NH3, hybridization equal to surrounding atoms 3 plus half into group number minus valency with respect to hydrogen same number, that is 4, Sp3. This Sp percentage of S character is 50%. 50% of S character. Next here percentage of S character 33.33%. Next Sp3 percentage of S character 25%. Therefore option will be B. So this is the end of chapter. In next video I will explain one more chapter. Thank you.